practice exam for the final exam, problem 11. Find the magnetic field everywhere for a spinning charged cylinder when the charge density is a function of the distance from the center of the cylinder. So it's given simply as Ks, where S is measured as the distance from the center of the cylinder. In order to do this, we're going to use Ampere's law. And so Ampere's law starts out with the Maxwell equation. The curl of the magnetic field is 1 over mu naught. Sorry. Magnetic field is equal to the current density, and here we're going to have to use the fact that the current density is the charge density times the velocity. Now for us, we know that the velocity is simply omega s, and it's going to be in the phi hat direction. It's going to be curling around that direction, and so at this edge, when it goes back into the page like this, that's the phi hat direction. So taking this expression, the Ampere's law is just the fundamental theorem of curls when applied to this thing. And so this is going to give us that the path integral over some closed path, dl dot the magnetic field, and I'm going to move the mu naught to the other side, will be equal to mu naught times the integral d2x of n hat dot j. And now we have to figure out what the Amperean loop we want to draw is. Well, we've done this. This is just a solenoidal problem, but it's slightly more subtle because we have a volume charge density instead of a surface charge density, but we're going to use the same Amperean loop. We're going to draw a loop like this. The surface is defined here. The normal to our surface, the way we have this, our n hat is equal actually in the minus phi hat direction, because the normal to the surface is going to point out of the page, not into the page. So the n hat is in the minus phi hat direction. We will say that the distance to the inner surface is s, and we're just going to ignore the outer one, because we know, we've done enough of these problems, we know that the magnetic field outside a solenoid is 0. Okay? And so there are many ways to do that. You can either place both of these outside, let one go to infinity, or you can make this go through the center of the loop, and then the total current going through, of course, has to be 0. And so magnetic field on that side and on that side have to be in, well, they should have to be in the same direction because we have azimuthal symmetry. The only way for them to be in the same direction and add to 0 is for them to be absolutely 0. So there we go. In any case, that's what we're going to use. So the other trick that we have is we have to figure out what it is this is. So the only thing that matters for us, right, is we have current that will go through the surface between S and A. And so we might think of slicing this into some thin slice right here that we'll call this distance S prime and has width ds prime. And so now that helps us write down what this volume integral here is going to be. So on the right hand side, doing the loop integral, you're going to have the 4 terms. You're going to have the term going down, the term going up, and the term going out, and the term coming back in. And so we could write that if we wanted to, but we're going to actually simplify this a little bit more. We're going to say, because of symmetry, I know that B, as a function of R, because I have this azimuthal symmetry, I know it's only going to point in the z direction, and I know it's only going to point out, it's only going to depend upon the distance s out of here. So when I have this dl.b on the top and the bottom, they're not going to contribute. And so what I'm going to get is the z hat's in the positive direction, so I'm going to get minus L times bz at s, and then plus L bz at this outer edge. But again, we know, because we've done these problems before, that that's 0. So we're just going to set that to 0 immediately. And that evaluates the left-hand side of Ampere's law. Now for the right-hand side, we're going to get mu naught. When I plug this in here, I see that my J is equal to rho omega S squared, right? Because I have a ks rho k omega S squared, so I have ks, and then the velocity is omega S in the phi hat direction. The n hat is a minus phi hat, so minus phi hat dot phi hat, I'm going to get a minus sign, so I put a minus sign there. Then I have to integrate over the volume. The volume is going to have this distance L in it, right, or the area, so it has the distance L. And then I have to integrate from S to A ds prime of this k omega S prime squared. So this is a trivial integral to do. First of all, I see that the minuses go away, the L's will go away, and this says that Vz as a function of S should be, we get mu naught k omega over 3 a cubed minus S cubed. And there we go. And so that's our magnetic field inside the cylinder. Writing it in general in vector form, so plugging this back in, we have two parts. We have this solution, mu naught k omega over 3 a cubed minus S cubed in the z hat direction, as long as S is less than A, and we have 0 if S is greater than A. And so that's the magnetic field everywhere for this spinning charged cylinder.